Namaskar. Today we talk about electrochemistry few topics. In today's lecture we discuss about the variation of conductivity and molar conductivity with concentration. The second topic that we discuss today is the Kohlrausch law of independent migration of ions. And the last topic, that is a application of Kohlrausch law. So these three topics one by one we start to discuss in our today lecture. We begin it. Variation of conductivity and molar conductivity with concentration. We start this topic. As we know, conductivity always decreases with decrease in concentration because the number of the ions in per unit volume decreases. So conductivity decreases. Don't merge it with conductance. Conductance increases but conductivity decreases because conductivity depends on number of the ions those are present in a unit volume. By dilution process, the number of the ions in unit volume decreases, so conductivity decreases. Molar conductivity increases with increases concentration. Why? Because according to the formula, lambda m is equals to kappa by C, and 1 by C, reciprocal of C, is known as the dilution. So our formula is a lambda m is equals to kappa into V. By dilution process, value of the V increases, so lambda m increases. Molar conductivity increases because the number of the ions are increases. Molar conductivity depends on number of ions in the whole solution. On the other hand, conductivity depends on number of the ions those are present in unit volume. When concentration approaches zero, that means infinite dilution, that is the stage of infinite dilution, the molar conductivity is known as the limiting molar conductivity, and it is represented by the symbol lambda m 0. This 0 is indicating zero concentration or infinite dilution. The variation in lambda m with concentration is different for strong and weak electrolytes. For strong electrolytes, lambda m increases slowly with dilution and can be represented by an equation. That equation is known as Debye-Huckel-Onsager equation, and the equation is lambda m is equals to lambda m0 minus a under root c. Now look, in this graphical representation, we draw this graph for the KCl. KCl, that is a strong electrolyte. A graph is between under root concentration and lambda m, that is the molar conductivity. Now on the x-axis we have taken concentration, on y-axis we taken molar conductivity. The value is like this: 0.1, 0.2, 0.3, 0.4 and the 0.5. These are concentration value. When we move in this direction, it means the concentration decreases. That is the indication of we are increasing volume by addition of solvent like water. It means that we are adding more and more solvent in that given electrolyte solution. We are adding more solvent, more dilution, so concentration is decreases. For the strong electrolyte like your KCl, when we increase dilution or decreases concentration. The value of KCl lambda m is increases very slow. That is increases very slow. When we compare this equation, when we compare Debye-Huckel-Onsager equation, it is the equation of straight line. According to the straight line equation, y is equals to mx plus c. On the y-axis, we have taken lambda m. On x-axis, we have taken under root c. This c is known as the constant. In this equation, this one is the representing c, lambda m0. That is known as the intercept of this graph. And this a is representing by this one in equation m. M mean gradient. Gradient is the slope of this curve, and the slope of this curve is minus a. Slope of this curve is minus a. So this is the graphical representation for a strong electrolyte like your KCl. The value of the constant A for a given solvent and temperature depends on the type of electrolyte. That is the charge that is present on cation and anion after the dissociation in solution. So the value of the A depends on nature of electrolyte. Now look, this is the graph for strong electrolyte and weak electrolyte. When we represent strong and weak electrolyte, for the weak electrolyte, what happens when we increase the dilution, the value of lambda m is increases exponentially. The value of lambda m increases exponentially. So there is a sudden change, sudden spike in the value of lambda m by increasing dilution. If we want to know the lambda m naught mean infinite dilution or zero concentration. Practically infinite dilution and zero concentration is not possible. But with the help of a graph, we can easily find out the value of any electrolyte for lambda m0. The method is known as extrapolation. By extrapolation method, we find out value for the KCl like this. Now this line is intersect here. So this one is the value for the KCl. But in the case of weak electrolyte like your acetic acid, this line is parallel to y-axis. So extrapolation method doesn't work in the case of weak electrolytes. By the extrapolation method, we can find out infinite lambda m0 value for strong electrolyte only, not for the weak electrolyte. Weak electrolyte like your acetic acid, those have the lower degree of dissociation at the higher concentration, and when we decrease the concentration and increase the dilution, on that time the degree of dissociation increases and the number of the ions are also increases. In such cases, lambda m increases steeply on dilution, especially near lower concentrations. Therefore, lambda m naught cannot be obtained by extrapolation method to zero concentration, or that is also known as the infinite dilution, because infinite dilution and zero concentration is practically impossible. Now look for the Kohlrausch law of independent migration of ions. Let's we discuss about it. Kohlrausch examined lambda m naught value for a number of the strong electrolytes and observed certain regularities. He noted that the difference in lambda m naught of the electrolytes those possess common ion in nearly constant. These are the values for some cation, and anion is written lambda m naught. With the help of this table, we try to understand Kohlrausch law. Now look in this example, which one is the common? Now look in this side K and Na, in this side also K and Na. So we are going to find out the difference of potassium and sodium molar conductivity at infinite dilution for the different electrolyte, that is the constant or not. With the help of the table, we put the value of KCl, NaCl, KBr and NABr. By solution of this, we obtained that the value of LHS side and RHS side is same. 23.4 is equals to 23.4. Now we more elaborate it with help of one more example. In this example, anions are common, OH and chloride ion. In this side again the OH and chloride ion. With the help of table, we put the value of NaOH, NaCl, KOH and KCl, and after the calculation we obtained that 122.8 is equals to 122.8. So this is known as the Kohlrausch law. It's known as the Kohlrausch law. Kohlrausch law say that the difference is nearly constant for the electrolytes. Kohlrausch law is given for strong electrolytes. Now with the help of this example, practical, we try to understand the Kohlrausch law. What happened? Observe that we have the two conditions. The first condition is this one and this one is the second condition. In the first condition, low dilution. In the second condition, dilution is high. We add more amount of solvent. Look in the first condition. In the first condition, these are the particles, those are dissolved. And this particle is the undissolved electrolytes. When we add more amount of the water, what happens? The more electrolyte is dissolved. After the addition of water, in this one, the whole electrolyte is dissolved. There is no undissolved electrolyte is present in second case. If you add more amount of the water, then what happens? The number of the ions doesn't increases. Why not increases? Because there is no undissolved electrolyte is present. The whole electrolyte is present in dissociated form. So it is not matter how much water you add in it. You add water. By n time, there is no change in molar conductivity because there is no change in the ions. So in this case, every ion is free. This is known as the infinite dilution case. In this case, every ion is behave like a free entity. There is no attraction and no repulsion. Every ion contributing with 100% potential in the molar conductivity. So this is the main basis of Kohlrausch law. The Kohlrausch law of independent migration of ions states that limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and cation of the electrolyte. This is known as Kohlrausch law. Mathematical formula for the Kohlrausch law is lambda m0 is equals to V plus lambda plus 0 plus V minus lambda minus 0. V plus mean number of cations, V minus mean number of anions, V plus 0 mean limiting molar conductivity of cation, and lambda minus 0 mean limiting molar conductivity of anion. For a simple electrolyte like your AXBY, that is dissociate like this, X ions are form of A plus Y and B minus ions are formed in Y numbers. So for this equation, how can we rewrite the Kohlrausch equation? The lambda m0 is equals to the value of the V plus, for this one is the X. So X. Value of the V minus for this is the Y. So we write here Y. So this is the common representation for the electrolyte like your AXBY. Now with the help of more examples, we try to understand Kohlrausch equation for electrolyte like your NaCl. NaCl is ionized and form one Na plus ion and one Cl minus ion. The V plus value is the 1 and V minus value is also 1. The Kohlrausch equation for this one is the lambda M0 is equals to lambda Na plus 0 plus lambda Cl minus 0. Like your electrolyte Na2SO4 that produced 2 Na plus ion and 1 sulfate ion. So V plus value is the 2 and V minus value is the 1 because the 1 anion is produced. So Kohlrausch equation for this one is the lambda M0 is equals to 2. Why we wrote here the 2? Because the 2 cations are produced by sodium sulfate. So 2 lambda Na plus 0 plus 1 lambda SO4 2 minus 0. For the calcium sulfate like that produce Ca plus 2 ion and sulfate ion. V plus and V minus values respectively are 1 1. So the equation is lambda M0 is equals to lambda Ca plus 2 0 plus lambda sulfate ion 0. For like your AlCl3 electrolyte that produced 1 aluminium ion and 3 chloride ion. So V plus is 1 and V minus value is 3. Kohlrausch equation for this one is lambda M0 is equals to lambda Al plus 3 0 plus 3 lambda Cl minus 0. Why we wrote here the 3? Because the 3 chloride ions are produced by aluminium chloride. So by this method we can write the Kohlrausch equation for various electrolytes. Applications of the Kohlrausch law. There is a various application for the Kohlrausch law. The Kohlrausch law is given for the strong electrolyte, but the help of the Kohlrausch law we can easily find out the lambda m naught value of a weak electrolyte. We can easily find out for a weak electrolyte because the lambda m value we cannot be find out with the graphical method, the extrapolation method. So with the help of Kohlrausch law we can easily find out. Next one is the degree of dissociation alpha, solubility of springly soluble salt and dissociation constant for a weak electrolyte. One by one we see the applications of Kohlrausch law. Let's start. The first is the lambda m naught for weak electrolytes. Now for example we have a weak electrolyte like your acetic acid. In the short form acetic acid is written as a HAC. Your weak electrolyte is ionized like this H plus and Ac minus. Kohlrausch equation for this one is lambda M0 for acetic acid is lambda H plus 0 plus lambda Ac minus 0. Let this is the equation 1. As in the formula you see this acetic acid generate H plus ion and acetate ion. So we take an strong electrolyte that can generate H plus ion. For this one we take HCl. HCl is a strong electrolyte that also generate H plus ion. So for the HCl the Kohlrausch equation is lambda M0 for HCl is equals to lambda H plus 0 plus lambda Cl minus 0. Let this is our second equation. Again look in the acetic acid that generate H plus ion and acetate ion. For the H plus ion we have already taken HCl. For the acetate ion so we take a strong electrolyte that can generate acetate ion. So for this we have taken sodium acetate. That sodium acetate is like this and the Kohlrausch equation for the sodium acetate is lambda Na plus 0 plus lambda Ac minus 0. This one is equation 3rd. Now in this equation by taking HCl and sodium acetate we require H plus ion and acetate ion only. So in this one extra ions are come. Which extra ions are coming? Na plus ion and Cl minus ion. So in next electrolyte we take that is the NaCl. NaCl is ionized like this and the equation is for NaCl is lambda Na plus 0 plus lambda Cl minus 0. Let this is the equation 4. Our next step is we add equation 2 and 3 and subtract equation 4 from that. Why we add 2 and 3? Because we require H plus ion and acetate ion. Those are present in acetic acid. And why we are subtracting equation 4? Because we doesn't require Na plus ion and Cl minus ion. So by this one we got equation like this. We are subtracting equation 4. So minus sign. We are subtracting the equation 4. So this one is turns in a minus sign. By calculation of this one, look, this one quantity is cancelled by this quantity and this quantity is cancelled by this quantity. So which one is the remaining? H plus ion and acetate ion is the remaining. So we can write this equation again like this. Now look, this one is the equation 5. Now compare your equation 1 and equation 5. For the equation 1 and equation 5, RHS side is same. If RHS side is the same, then we can say the LHS side is also same. So for lambda m, acetic acid is equals to lambda m HCl plus lambda m naught sodium acetate minus lambda m0 NaCl. So by this equation, we can easily find out a weak electrolyte like acetic acid, the molar conductivity at infinite dilution or zero concentration. With the help of numerical, we try to understand more. Lambda m naught for NaCl, HCl and sodium acetate are respectively given. Calculate the lambda m naught for acetic acid. So we arrange all the value in a tabular form. These are the values. Recently we derived this formula. When we put the value in this formula, we got the lambda m naught for acetic acid is 390.2 Siemens centimeter square mole inverse. Now the next application, degree of dissociation, that is the alpha. The degree of dissociation is find out by this equation. The alpha is equals to lambda m at any concentration divided by lambda m0. Lambda m0 mean at infinite dilution. So lambda m at any concentration of the electrolyte, that is divided by the lambda m0. This ratio is known as the degree of dissociation. The same way, we can easily find out the dissociation constant for this one. The dissociation constant according to the Ostwald law of the dilution equation. The Ka is equals to alpha square into C upon 1 minus alpha. We find out the value of the alpha by this method. And the value of the alpha is put in this one. The concentration C we know, and we find out the value of Ka, that is the dissociation constant. Now the solubility of this salt. Such salts like your AgCl, barium sulfate, lead sulfate, those are very less soluble in water. That is also known as the springly soluble salts. So for that one, we find out the first molar conductivity. Molar conductivity is equals to kappa into 1000 by C. The molar conductivity, with the help of molar conductivity, we can easily find out the value of the C. The value of lambda m for such salt we find out with the Kohlrausch law. For the such salts, we find out the value of lambda m with the Kohlrausch law. That value we put in this equation and we obtain the value of the C. C mean concentration, that is the molarity. Molarity mean mole per liter. So that is the again is a solubility. That is a type of solubility, and the unit of that solubility is mole per liter. If we find out the solubility in the gram per liter, then we multiply this concentration with molar mass. That tell us about the gram per liter solubility. So these are the applications of Kohlrausch law. Now with the help of a numerical, we try to understand more. Conductivity of 0.00241 capital M acetic acid is 7.896 into 10 to the power minus 5 Siemens centimeter inverse. Calculate its molar conductivity, and if lambda m0 for acetic acid is 390.5 Siemens centimeter square mole inverse, what is its dissociation constant? So the value or the given we write like this. Concentration is the given, kappa is given, and lambda m naught value is given. First we find out the molar conductivity. According to the formula, the lambda m is equals to kappa into 1000 by C. We put our value of the kappa and value of C. By putting this value, we find out that the lambda m is equals to 32.76 Siemens centimeter square mole inverse. Now next, we find out the value of degree of dissociation. According to the formula, alpha is equals to lambda m by lambda m0. Lambda m, recently we find out 32.76. Lambda m0 value is given 390.5. By calculation, the alpha is 0.08389. This is the degree of dissociation. Now the question is arise, why we find out the degree of dissociation? Because without the degree of dissociation, we cannot find out the dissociation constant. According to the formula, the dissociation constant is K is alpha square into C upon 1 minus alpha. So we should have the value of alpha. Now we put the value of alpha and C in this equation and we calculate the value of K is comes out 1.85 into 10 to the power minus 6. So this one is our correct answers of this numerical. Thank you for patiently listening me. Next time we meet with a new topic.